In this video, we will look at the theory behind the water distribution models. To start off, we need to know that the water distribution models computes the hydraulics of the system for steady-state situations. If a system or process is in steady state, it means that it does not change over time. You can think of it as a snapshot of the system at a specific time. We will talk more about the types of simulations later in this course. Now that we know that the water distribution models calculate the steady state of the water distribution systems, we can introduce the laws that are used to do the hydraulic calculations. These are the Kirchoff's laws. I'm not sure if I'm pronouncing that correctly, but that's how I say it now. These laws are known in the studies of electrical conduits, named after German physicist Gustav Kirchoff. But they are actually used in the water distribution modeling softwares because the principles of conservation of mass and energy in fluid systems are directly analogous to Kirchoff's laws used in electrical circuit analysis. Water distribution models are mostly built up by nodes. These are also called junctions and links. Links represent the pipes, but the nodes do not solely represent manholes. Often will a node represent the manhole, but in many cases, one needs several nodes to represent a manhole. Kirchoff's first law states that the total flow into a node equals the total flow out of the same node. This one is pretty intuitive. Kirchoff's second law, also called the law of conservation of energy, states that between any two nodes, the head loss is independent of the path taken. This means that the sum of all head losses along pipes that make a complete loop equals to zero. For both of these laws, we need to be aware of sign conventions. You can choose what you want, but you need to be consistent with your choice. If there are more than one reservoir, meaning water sources, there is the relationship that the sum of the friction losses along the link between the reservoirs is equal to the elevation difference between the reservoirs. These are called pseudo loops. These laws or relationships are the basis for the computations that modeling softwares do. When we have a water distribution system, we can calculate the number of equations as shown in this example. We have 8 nodes and 1 reservoir, so we get 7 node equations. We have 8 links and 8 nodes, so we get 1 loop equation. Lastly, we have 1 reservoir and therefore 0 pseudo-loop equations. Like in most modeling endeavors, we need boundary conditions. And to simulate the steady state for a water distribution system, we need information about outflows or inflows in our system. These outflows are typically water demand from different water uses, and most often, some of this water demand is due to leakage, which we will also be addressing in future videos. In addition to this, a steady energy head at one node is required. Lastly, we need a starting situation for the flow in the pipes. To set up this, we can use the node equation, also known as Kirchoff's first law. So how is this done? Well, let's say we have this system. We have a steady energy head here and the outflows here. Using the node equation, we can calculate our way backwards towards the reservoir. Here is one starting point for the flow regime in the system with these boundary conditions. And here is another one. So we have these laws that relates the continuity balance and the energy balance. How does the modeling software work? Well, we have our system with a number of nodes, pipes, and reservoirs. We know a lot about our system, or should know a lot about it nevertheless. For example, we know the demand at the nodes, we know the properties of our system, for example, the pipe diameters, lengths, materials, etc. But we do not know the energy head at each node, and we also don't know the flow in the pipes. So, in order for the modeling softwares to compute the unknowns, a method to describe the topology is needed, and a system for handling the sign convention. To achieve this, an incident matrix is used. For example, for the node continuity equation, we have the A component here, which is part of the incident matrix, capital A, and Qi, which is the flow in the pipe segment I. The O component here is the outflow from node J. A typical incident matrix can look like this. The pipe goes this way, following the columns of the matrix, and the nodes represent the rows of the matrix. Let's say we have this system. Then we have the following continuity relation as shown in this matrix multiplication. Let's break this down. I think it is easier to see this from the node perspective. The first row is node 1, the second row is node 2, etc. If we take node 1, for example, we see that link Q1 goes into this node. Therefore, we put a 1 here. Remember the sign convention? 1 is into a node, -1 is out from a node, and 0 means that the pipe and the node are not connected. While we are still at row 1, meaning node 1, we move to the next column, which is pipe Q2. The pipe goes out of the node, and by our sign convention, we put a -1 here. Link Q3 and Q4 are not connected to node 1, and therefore we put a 0 at these places in the matrix here. Just to make this real clear, we'll go through node 2 together as well. In node 2, link Q1 is not connected, so this becomes a 0 in the matrix. We then have Q2 going into the node, this becomes a 1 here, and then we have Q3 and Q4 going out of the node. So therefore we set these as -1 in the matrix here. The 1/4 matrix with the small q here represent the flow in the pipes, and the 1/4 matrix here with the component O represent the demand or outflows from the nodes. If we do the matrix multiplication, we get this. And if you don't remember or are unfamiliar with matrix multiplication, it is pretty simple. We take the first row in this matrix and multiply it with the column in this matrix. For each component that we multiply, we add them together. Therefore, we get 1 times Q1 like this. Then we add and multiply -1 with Q2. Then we add the 0 times Q3 here. And lastly, we add the 0 times Q4 here. So for the next row in the incident matrix A, we do the same. 0 times Q1 is added to 1 times Q2, which is added to -1 times Q3, which lastly is added to -1 times Q4. This goes on until we have gone through every row in our incidence matrix. If we clean up the equations, we get the following. For the equation for the node 1, we get Q1 minus Q2 equals O1. For the equation for node 2, we get Q2 minus Q3 minus Q4 equals O2. Q3 is equal to O3 and Q4 is equal to O4. This gives us that Q1 equals Q2. Q2 equals 5 plus Q3 plus Q4, which again is 5 plus 20 plus 10, which is 35, because we already know that Q3 is 20 and Q4 is 10. So we have a scheme for the continuity equation using this matrix system. The simulation software also needs to calculate the energy losses. And the main energy loss in the system is through pipe friction. By using a resistance factor, we can denote the change in energy in the system through each link using this relationship. Delta E equals RF times Q to the NF. So a matrix equation is set up that accounts for both the continuity aspect, but also the energy balance. The matrix equation is then solved linearly if the incident matrix is symmetrical. And if it's asymmetric, a numerical approach is used to solve the equations. There exist many numerical approaches to solve the equations, for example, the Hardy-Cross method. EPANET, which many of the commercial modeling softwares are based on, uses the gradient method put forth by Taudini and Pilari. Well, this was a little peek at the theory behind water distribution models. I think it is good to have some insights to what is done in the models when simulating the systems. This can make us more confident when evaluating the model results. In the next video, we will be looking at the modeling software which we will be using throughout the rest of the course when we will be doing practical water distribution modeling. It's gonna be great, so stay tuned for that. And subscribe to the channel if you find this content useful. Have a nice day, and I'll see you soon.